Hello and welcome to section 5.3 on antiderivatives and the indefinite integral. We have calculated the derivatives of many functions. In this section, and the general theme of the remainder of this course, we attempt to reverse this calculation. That is, for a given function f, are there functions whose derivative is f? Graphically, when the derivative of a function is given, we are able to sketch an approximation of the original function. The problem is, having information on the instantaneous rate of change does not give information on the y values of a function. For example, knowing that a car is traveling at 40 miles an hour does not help determine its position on a highway. We analyze this graph with the knowledge of Chapter 3 at our disposal. We see that the roots of the derivative at x equals 2 and x equals 3 are where the function has a horizontal tangent line. These roots divide the domain into intervals, on which f is increasing or decreasing. As the derivative is positive between 2 and 3, the function is increasing on that interval. As the derivative is negative between 0 and 2, and then again after 3, the function is decreasing on these intervals. We can sketch the function of f with this information, but we do not know where to pin the graph of the function. That is, we do not know the y values of any point on the graph. As this is a sketch, and we cannot find the y values, we assume that the function begins at the origin. Then the function decreases at a quickening pace until x equals 1, and then the decreasing slows until the function has a horizontal tangent line at x equals 2. Then the function increases from 2 to 3 and hits a horizontal tangent line at x equals 3, and then the function decreases at a very slow rate. Eventually, the function is barely decreasing, approaching a zero slope. Keep in mind, this is only a sketch, and one in which we are not sure of any of the actual y values. I have graphed 3 possible f's, but the actual graph has the possibility to be pinned at an infinite number of points. We now move from a graphical to more algebraic analysis of antiderivatives. A function big F is called an antiderivative of little f on an interval I if the derivative of big F equals little f for all x in the interval I. For example, take sine x as big F and cosine x as little f. The derivative of sine is cosine, so sine of x is an antiderivative of cosine x. In section 4.3, the mean value theorem was used to show that two functions with equal derivative were the same, but up to a constant c. This leads us to the definition of a general antiderivative. Once you find an antiderivative big F for little f, then every antiderivative will be of the form big F plus c, where c is any constant. Now, because the derivative of sine is cosine, every antiderivative of cosine has the form sine x plus c. We will now find the general antiderivatives for the functions which serve as the building blocks of elementary functions. We just calculated the general antiderivative for cosine, but for most trigonometric functions, finding an antiderivative will prove difficult. We will not calculate an antiderivative for tangent and cotangent until section 5.7. And the derivative of secant and cosecant will not be calculated until the second semester of calculus. But we can reverse the standard derivatives of tangent, cotangent, secant, and cosecant to recognize them as antiderivatives of their derivatives. The first two functions on our list are not as simple to calculate as the bottom. The derivative of cosine is negative sine. Therefore, the general antiderivative of sine is negative cosine plus c. The derivative of x to the n plus 1, using the power rule, is n plus 1 times x to the n. If we assume that n is not equal to negative 1, then n plus 1 is not 0, which means that we can divide by it. Therefore, we can calculate the derivative of 1 over n plus 1 times x to the n plus 1 as x to the n. So we can reverse the power rule for the function x to the n when n is not equal to negative 1. The general antiderivative of x to the n, when n is not equal to negative 1, is n to the n plus 1 over n plus 1 plus c. You got to remember the constant. Since the derivative of a sum is the sum of the derivatives, the antiderivative of a sum is the sum of the antiderivatives. In a similar way, the antiderivative of a constant multiple is a constant multiple of the antiderivative. Therefore, we can calculate the general antiderivative of the function 4 times cosine x plus 3x squared. We first ignore the constants, taking the antiderivative of cosine, which is sine, and the antiderivative of x squared, which is 1/3 x cubed. We find that the general antiderivative is 4 sine x plus x cubed plus c, where c is any constant. Be careful with antiderivatives. It is not only a matter of applying a formula to calculate. In fact, there is not a product rule or a quotient rule for antiderivatives. Finding an antiderivative is more of an art than calculating a derivative. Take for instance the function 1 over x squared and 1 over x squared plus 1. As 1 over x squared is really x to the negative 2, and negative 2 is different than negative 1, we know how to calculate the general antiderivative. We're just reversing the power rule. We add 1 to the power and then divide by that new power. Now, the general antiderivative of 1 over x squared plus 1 is arctangent of x plus c, because the derivative of arctangent is 1 over x squared plus 1. Notice, a tiny change in the denominator creates a large change in the antiderivative. But don't worry, our antiderivatives will not become too complicated until we get to the second semester of calculus. Suppose a ball is dropped with an initial velocity of 0 meters per second from a building which is 100 meters tall, and imagine wind resistance is irrelevant. Find the function representing the height of the ball with respect to time. We assume that the only force acting on the ball is gravity, which accelerates the ball at negative 9.8 meters per second squared. Since the derivative of velocity is acceleration, the antiderivative of acceleration is velocity. Reversing the power rule for derivatives, we find that the velocity of the ball is negative 9.8 t plus c for some constant c. In the problem, we were told that the initial velocity at time 0 was 0 meters per second. So 0 is equal to v of 0, which equals negative 9.8 times 0 plus c. So the constant c is 0. The derivative of height is velocity, so the antiderivative of velocity is height. We can calculate the general antiderivative of the velocity using the power rule in reverse. And in the problem, we're told that the initial height of the ball at time t equals 0 is 100 meters, which tells us that c is 100, and we have calculated the height of the ball. The general antiderivative of a function is represented by the indefinite integral, a useful notation which will become more clear once we have discussed the fundamental theorem of calculus. You've seen the basics, now work towards mastery through practice and study.